it will be a semigroup. So now one can create a simple random walk on the RNFest cube as a semigroup of random unitary operators in RM with discrete time parameter. So, by the way, here we have a new possibility. Because let me recall you that we start with the question, what happens with coalescing independent random walk on RNFest cube. But it can be easily checked that if we will start from arbitrary initial positions and then make the number of direction of freedom goes to infinity, we never will meet. So in the end, so we have to make some pushing, and here we have new possibility because we now discussing operators, not points in the space. We do not need to say, okay, these 2 points coincide if they have the same position in the space. No, now we have operators, and one can glue up operators on growing subspaces. So we just can, in our language of random walks, we just can check whether they coincide on some coordinates. Not totally, but on some coordinates. So now the question of what we have, what is the space in the limit, what we will have. And of course, we can start from Bernoulli variables, and I did it previously, but now I think it is not necessary. So let's start from the sequence of independent standard Gaussian variables. And for any m, define the random element xi m in L201 by the formula. Here is the formula. We just have a random step function, which is organized from the intervals from the uniform partition of the 0, 1, multiplied by the standard independent normal Gaussian variables and the square root of m, just normalization. Then, what is the scaling? Now it is trivial. It can be easily checked that xi m weakly converges to white noise in L2 no, 0 m 0, 1 when m tends to infinity on the finite subset of h. H is this is L201. So we have just the following convergence for any finite number function. It is trivial. And now one can define the semigroup Xn on the space L201. You remember, we started from the unitary operators on Rn, but we can easily extend it to L201 as follows. For X, which is which is element of RNFest cube, and function f from 201 put xft is equal to again multiplication on the coordinates of x, but we multiply on xk on the interval k over n, k plus 1 over n. So this is again some rotation, and we have this this representation. Oh, sorry, it must be not n but m, the same m as power of cube. So in this way, what we get? In this way, we get the family or 1 stochastic semigroups with discrete parameters in L2, 0. Now one can try to organize a limit, what we will have when m tends to infinity. What we will have as a scaling limit of this stochastic semigroup. And here it is very important how do we organize the random walk on the Ehrenfest cube. As we remember, on every step, we just randomly and uniformly take one of the coordinates and change sign. Here we do not make difference between coordinates of x. This leads to the very interesting, from one point of view, but from another point of view, very hopeless conclusion. Here is it. Let me, oh, excuse me. Oh, no. Here it, let me, oh, okay. It occurs that when m and n tends to infinity, we do scaling. Suppose that n over m tends to some lambda, positive lambda, then for any functions f and j, which belong to L201, such action of our unitary operator at the time here is integer part of nt, so we do nt steps approximately. Multiply, so this is bilinear form of this operator. Let me recall this unitary operator. But in probability, it converges to very simple number. This is e in power minus 2 lambda t fj. So we see interesting phenomenon. We have a family unitary operator, but they weakly converge, only weakly converge to such trivial operator like trivial semigroup. You see, it even is not stochastic. We just forget all randomness in the limit. After scaling, we get the following very simple semigroup. The same happened. I did not wrote it because it is very similar. The same happened if we consider different procedures when we try glue up the family of random walks on the Ehrenfest cube. We'll get in the limit deterministic semigroup, which with different here we can have instead 2 lambda we can have different number. So after scaling of random walks on Ehrenfest cube and application to white noise, one can get family of correlated Ornstein-Uhlenbeck processes. That's all. Only correlated very simply, like this, with some exponent. That's all. This is answer. So now we understand completely what happened in Ehrenfest model when we are trying to organize a family of coalescing random walk and then scaling when the number of directional freedom goes to infinity. And let me again emphasize what is the reason on such pure picture in the limit. As I said, the reason is the following. We do not make difference between the coordinates of x. So at any moment of the time and at any step, we just randomly choose any coordinates. So any coordinate. This leads to the following phenomena. We like take a dust uniformly on our interval. And when time goes on, so we have just this level of the dust, E minus 2 lambda t. That's all. So the law of large numbers work. Then the idea is following. We can forget about such RNFS approach. Just pay attention every coordinate. And then we get a new picture. We can glue up white noises, just considering random stochastic, random semi-group of operators, and glue up noises with the help of this semi-group of operators. Then we will get much more rich and much more interesting picture. Excuse me. Okay, so okay, this is okay. So let me begin with the following. Suppose we have a white noise. Here is the definition of white noise in Hilbert space with covariance operator S. S does not need to be a nuclear operator. It's just bounded self-adjoint operator. Then we have white noise. It is easy. The scalar product with the element of H has normal distribution with SHH as variance and MH as mean. One can consider an example. For example, here is Ornstein-Uhlenbeck process based on the family of operators, unitary operators, or even not unitary, but operators which has norm less or equal than one. One can construct such Ornstein-Uhlenbeck process using the family of independent white noises eta n. To do this in the continuous time, we need the notion of stochastic semigroup. By the way, notion of stochastic semigroup of operators was introduced by Anatoly Vladimirovich Skorokhod, and he wrote two long and well-known papers, maybe in 83, 84, related to construction of stochastic semigroups of operators in Hilbert space. And so he gave not only the definition, but a very interesting example of this family. So for us, we just consider not unbounded operator, but operator which has this norm. I will suppose that they are commuting and so on, and they have evolutionary property. Sometimes they will have independent increments. So on different intervals of the time. This theorem, there exists a white noise process, psi t. What does it mean, white noise process? It means that for any t, psi t is a white noise pitch. Such that it has the following covariance. Here, J is T now is deterministic. So psi T is Gaussian. And this covariance completely describes its finite dimensional distribution. The idea of proof is the usage of spectral theorem for self-adjoint operators and do the same in one-dimensional case. Obtained process can be called by a generalized Torstein-Uhlenbeck process based on the semigroup. And by the way, if we have such very simple semigroup, you see, it is constructed from the function f. We just multiply on one the coordinates which is such that f is greater than t, and kill fx if t is kill such x if t is greater than f. Then there exists such white noise, and if we take fx is absolute value of logarithm x, then the process eta t is usual Ornstein-Uhlenbeck process with covariance. So we see that with this construction we can get well-known object. Based on the JST, one can construct coalescing white noise processes. For example, if phi is a covariance function of the two white noises in H, so it is defined as follows, then there exist two jointly Gaussian white noise processes such that we have the following mutual correlation. They correlate with J 0s1, 0s2, and here is the square root of 1 minus j. Remark: if JST are projection, then the subspaces FT increase, of course, and white noises coincide on FT. So we can construct white noise processes and glue up them on the increasing subspaces. You remember the problem from the Ehrenfest model. But now we can glue up on subspaces. We don't need to meet points. We just can glue up white noises on the subspaces. They can be finite dimensional or not. It depends on the semigroup. So the same can be done for stochastic semigroup of self-enjoined random operators. Here it must be mentioned. Here is the definition. I just recall that it has independent values on the disjoint interval, and it must be mentioned that Skorokhod in 83-84 describes the structure of such semigroup in case when expectation is invertible operator. Then he claimed that JST is just solution to linear stochastic differential equation in Hilbert space. But if this property fails, we can get absolutely different picture. So one can consider semigroup of finite dimensional projection. And here is the expression of such semigroup. We just kill coordinates accordingly to independent Poissonian noises. Then, based on this finite dimensional projection semigroup, one can build stochastic process, construct Ornstein-Uhlenbeck process of white noises, and consider the coalescing white noises, which will coalesce on the increasing subspaces. By the way, if this series converge lambda and t, then it can be checked that as exactly in the Aratia flow, we immediately will glue up our noises on the almost all coordinates except finite number. So the same effect as in Ratia flow. Here is just calculation of the joint covariance. It is not necessary to check it. So my claim in this talk is that firstly, in RNFest model, we have to create random walks as unit operators. Secondly, under scaling, if we don't pay attention to coordinates, don't distinguish coordinates, we get very simple multiplication on number semigroups in Hilbert space. Then, instead of this, one can consider stochastic semigroup, which pay attention to coordinates. By the way, this construction pay attention to coordinates. And then we get, instead of random walks, we can get the white noise processes which begin to coalesce on the growing subspaces of the Hilbert space. That's all. Thank you for your attention.
Thank you very much. We have time for maybe 1-2 short questions.
May I ask the first question?
Yes.
Andrei Anatolich, my question is the following. About the particle system, your preference was to identify it with unitary operators. But for instance,
Yes.
people who work with simple symmetric exclusion process, zero range process, and so on, usually they use, say, either sided measure or measures and so on. Here you also had that possibility. Maybe you can say a few words why you gave the preference to this way of description, and maybe describing via sided measures where you just put atoms, for instance, in some points with masses 1 and -1 also would work.
You see, of course, I consider this possibility. And as I said, in RNFest model, we have, we have the following picture. We just take how we make this new step. We uniformly choose one coordinate and change the sign. So what you will need? You will have signed measure. Suppose you put it on 0, 1. Yes,
Yeah.
and do uniform partition. Then you have -1, 1 uniformly distributed on these points. Yes, and then when you will make scaling, your signed measure will go definitely will go to 0. Because from the symmetry arguments, yeah.
Mm-hmm.
So this was the reason why I changed the mind and thought that maybe the trace we will get from the integrals. By the way, Vitaly, see this relation. Here is x and t f j. This is the integral. You can just say on another language. Okay, this is integral with respect to your signed measure. You see the limit. Yeah, it is very
Yes, it was exactly my question.
yeah, it is very
because I saw that.
But what we need more, we need some structure of changing of this guy with time. And now, as I said, xn in my interpretation became to be semigroup. So we, as a weak limit, we get semigroup. Of course, in this case, it is very simple semigroup, but it is. This also is a reason, because as I showed in the next part of the talk, the second part of the talk, we can make a much more rich construction. Yeah, if we take another semigroup.
Okay.
This was the reason.
Okay, thank you so much.
You're welcome.
Thank you. So if there are no more questions, then thank you very much again. And
Mhm.
we continue with the talk of Georgy Ryabov,
Mhm.
coalescing
me-
stochastic flows on metric graphs.
Mhm. Mhm.
May begin.
Yes.
Let me stop the demonstration of the screen. Oh, okay.
Okay, so I hope that you see my screen. In this talk, I will speak about stochastic flows on metric graphs and discuss the question when we can find a modification of a stochastic flow which is actually a strong flow. So first, I describe stochastic flows by transition functions that define distributions of finite point motions of flows. I give definition in a general case when the space is a locally compact separable metric space, and by Pn, I denote a sequence of failure transition functions. So Pn is a transition function on m to the power n that defines the distribution of endpoint motion from the flow. And these transition functions, they must satisfy first the consistency property that says that endpoint motions, they define k-point motions when k is less than n. Second is a coalescing property, which means that if we consider two-point motion such that both trajectories started from the same point, then they move together all the time. And the third property, which is a sufficient condition for continuity of trajectories of finite point motions. Okay, so when we have a sequence, such sequence of transition functions, then it is known that they define finite point motions of some stochastic flow on M. So this is a result of Lejeune and Raymond. So from the sequence Pn, one can construct a family of random mappings of M that satisfy these five properties. So the first one says that when we consider psi as a flow, then in fact endpoint motions of psi are given by transition functions Pn. So the second property is a flow property, and in this result, the flow property is satisfied almost surely. Almost surely, and the exceptional set depends on everything. So it depends on x, s, t, maybe not on u. Okay, also the increments of the flow are independent, and last two properties, they are analogs of a failure property of transition functions P. Okay, the question that I'm interested in is first how good modification of a stochastic flow one can find. For example, in general construction, there is even no measurability of psi in variables s and x. Okay, and second question is, can we find a modification that satisfies the flow property without exceptions? The approach
that we propose is based on the analysis of families of deterministic mappings with values in M. So first we will give a completely deterministic construction of a flow and then apply it to some stochastic flows. So I will consider continuous functions with values in M that start from that are defined on an interval from S to infinity for different S. Okay, and theta Sx starts from x at, let's say, at time S. Okay, by a skeleton, I will understand a sequence of continuous functions phi n. They start from different times Sn in such a way that moments of start, moments and positions of start, Sn phi n, Sn, form a dense set in R times M. Second, when two functions from the skeleton, when they meet, then they stay together. And the third property is the most technical one. So it says that if we consider a compact set in the product of R and M, and consider all trajectories from the skeleton that at some time arrived to this set, and consider their restrictions after this time. So some trajectory hits this set, and then we consider the restriction of this trajectory after the hitting time. So the condition is that these restrictions, they form a relatively compact set in the space of continuous functions. Relatively compact with respect to topology of uniform convergence on bounded sets. Okay, so when we have a sequence of such functions phi n, I will call it a skeleton, and we can think of it as a part of the future flow. So what I will do is I will try to recover the flow from the skeleton. So by S, I denote the space of all skeletons. And this space, actually, the trajectories from the skeleton, they live in the space of continuous functions. So I denote it by X. It is continuous functions with values in M that start from all possible moments of time S. It is a complete separable metric space when the metric is a metric of uniform convergence of graphs. Okay, then a skeleton is a subset of sequences in X, and I will use two facts. The first one, it follows from compactness condition and states that for any S and any delta, values of the skeleton at time S of trajectories that started like after S minus delta form a dense set. So again, it is a consequence of that compactness condition. And another property that I will use is existence of a measurable selection mapping So it is like a fact that there exists a measurable mapping that to any sequence of functions from X that maps into another function, such that if a sequence Fn is relatively compact, then the value L on this sequence will be a limit point of this sequence. So this mapping chooses limit points of relatively compact sequences in a measurable way. Okay. Next, let us fix a sequence of measurable functions on M that pointwise decrease to 0. Using this sequence, we will define like approximations of trajectories from the flow in the following way. So for fixed S and X, by N and K, I denote the number of the first trajectory of the skeleton that was at distance epsilon k from X at time S. Okay, and by phi k, I denote the restriction of this trajectory from the skeleton after time S. So in such a way, for each S and X, we define a sequence of approximating trajectories from the skeleton. Okay, and now let's just apply this measurable selection to the sequence phi k. From our assumptions, phi k is must be relatively compact. So what we obtain is some limit point, some limit the trajectory of this sequence phi k. Okay, and in such a way, we define some continuous trajectory for all S and X. In other words, we obtain a mapping that for each S, X, and each skeleton returns some continuous function. It is a measurable mapping. Its value on S and X is a continuous function that starts from X at time S. And this mapping preserves trajectories of the skeleton. So if Sx belongs to the skeleton, then the mapping will return the restriction of trajectory of the skeleton after S. So in such a way, we turn a sequence of continuous functions into a family of continuous functions that starts for all times S and X. Okay, so this defines an extension of skeleton, and this extension satisfies the flow property along the skeleton. However, at other points, the flow property for theta may fail, and the reason is a possibility of existence of bifurcation points. So now I will define what it is. So first, KST of X is the closure of all trajectories from the skeleton on the segment ST that were in the epsilon neighborhood of X. Okay, so we consider X, consider its neighborhood, and look at all trajectories from the skeleton that were in this neighborhood. Okay, then take the closure with respect to a uniform distance. Okay. From our assumption, this set is a non-empty compact set. And when we intersect it in epsilon, we get again a non-empty compact set of continuous functions on the segment ST. And in fact, this set contains the restriction of a continuous function theta s, because theta s is a limit point of functions from the skeleton. Okay, and let nu be the number of elements in K. In fact, this quantity is quite complicated because nu can be infinite. Anyhow, let's excuse me. Now let tau be the infimum. So it is the first time after t such that nu st x is bigger than 1. Okay, so it looks like this. If we have x and at time s, if this is tau sx, then at this time we can have, actually we have a possibility for bifurcation. And the set of bifurcation points is defined as the set of times and positions Sx such that tau Sx is equal to S. So it is a set of points where we immediately can have a possibility for bifurcation. If t is less than tau, then we have a single function in the set kst x. And actually this single function is theta sx. Okay, and now let me describe a procedure that modifies the flow theta at bifurcation points. So let's fix some closed set F that contains a set of bifurcation points. And for every point Sx, define a sequence of times sigma and positions Z in the following way. Okay, so at 0, sigma is S and Z is X. And then each next value sigma is the first time that trajectory that started from the previous time sigma and previous point Z hits the closed set F. Okay, and Z is next Z is a position where it hits the closed set F. Why I consider set F instead of the set of bifurcation points is because the set of bifurcation points, actually we don't know how bad it can be.
Georgi, is it possible that sigma k plus 1 is equal to sigma k?
Exactly. And you see that the next line, what is KSX?
I see.
So K and K, yes. So sigma k is an increasing sequence, and it can be that sigma k is equal to sigma k plus 1. Then they all equal after this time, after this index. And k is the first such index if it exists. Actually, the definition of sigma and z depends on set F also. If, for example, F is the whole space, then all sigmas are equal. And okay, I consider closed set F instead of set of bifurcation points because, as I said, we don't know how bad the set of bifurcation points can be, and we need our definitions to be measurable functionals from the flow. Okay. And when we define this sequence of consecutive heating times, we modify the family theta into another family psi. Okay, so between heating times, we define psi as theta with a corresponding starting time sigma and starting point z. Okay, if k is finite, then if ksx is finite, then we define psi as the trajectory theta that corresponds to starting time sigma of k and starting point z of k. And the third is not interesting. Then for each s and x, we get a continuous function either when times sigma converges to infinity or when k is finite. And there are two assumptions that are sufficient for new family psi to be actually a flow. Two assumptions are, so the first is that all indices ksx are finite, and if ksx is 0, then function theta immediately coalesces with some trajectory from the skeleton. So for any t greater than s, theta coincides with the trajectory from the skeleton after t. So under these two properties, psi satisfies the flow property without exceptions, and as it was for theta, psi preserves trajectories of the skeleton. Okay, now let's apply it to stochastic flows. And actually, to apply it, I need to assume that if I have a flow, and if I choose like a part of the flow that starts from a countable dense set, then it must be almost surely a skeleton. And the only condition which may not be satisfied is that compactness condition. Let me maybe go back quickly. Okay, so when we have a stochastic flow, it is not known if this condition holds almost surely. Okay, so that restrictions of trajectories from a stochastic flow on a compact set, in some sense, yes, form a relatively compact set almost surely. Okay, so if we assume that it is true, then we can pick only trajectories that start from some dense set D. They will be a skeleton, so we can apply the construction. And if almost surely conditions of the previous theorem are satisfied, then psi gives a modification of initial stochastic flow that has a strong flow property. So it satisfies flow property without extensions, without exceptions. Okay, the question why psi will be actually a modification, it is the question of the choice of epsilon of these functions epsilon k. So epsilon k must converge to 0 fast enough, then what we get as a result of our construction will be a modification of initial stochastic flow. So some applications when okay, so some cases when we can apply this construction. First, on a metric graph, we can construct a strong stochastic flow of independent before meeting Walsh-Brownian motions that coalesce at the meeting time. Actually, in this case, theta is enough. Theta already will be a strong flow. And it is enough because in this example, theta has the instantaneous coalescence property. It means that if we look at values of the flow at time t, values of trajectories that started before time s, when s less than t, then such set will be locally finite. So with probability 1 for all s less than t. And this in turn follows from the following estimate on the meeting time. So the probability that two trajectories didn't coalesce during the time proportional to distance between them squared is uniformly bounded from above by something less than 1. Okay, so then I have no time, yes?
Well, you have 1 minute.
Okay, 1 minute. Then the last application is it's a quite simple example. It's a stochastic flow of solutions to Tanaka SDE, and it is interesting that existence of a strong flow modification follows from our general result, because in this case k is almost surely less than 3, which is a consequence of absence of multiple local extremas at the same level of a Brownian motion. Okay, and same results were also obtained for Tanaka flows on metric graphs and Birdzi-Caspi flow on the real line, and there are some other flows for which I think it can be applied, but it is a work under progress. Thank you for the attention.
Thank you very much. Are there any questions?
Georgi, do you know some information about this bifurcation set, possibility to have triple other trajectories after meeting?
We know examples from Brownian web where there are, I think, points of kind 1, 3, and so on. So, definitely it is a complicated set, so it is interesting to look at its structure.
In case of Brownian web, as far as I remember, the structure bifurcation points, the investigation of structure bifurcation points was heavily based on the law of iterated logarithm. So
Yes.
maybe here you can do the same.
Yes, maybe.
Okay.
Thank you. Any other questions? So maybe I also have a question. I just, you said that M is any locally compact metric space, right?
Yes.
So for example, it can be a 2-dimensional, 3-dimensional Euclidean space.
Yes.
And do you have an example of skeleton in such spaces?
You mean that two trajectories will meet?
No, just any example of maybe
but you
interesting
can take
example of skeleton.
you can take any flow, let's say even smooth flow.
Oh, you can take smooth flow, right?
Smooth
And you can
flow
have
and pick
skeleton.
countable.
Okay.
That's
Okay, thank you.
that.
Okay, if no
Yeah,
more
but
other
there are
questions.
also non-smooth
Okay.
flows even in the dimensions 2 and 3.
Okay, thank you. Yeah, so like I said, I'm just if there are any interesting examples.
Interesting class of examples is the Sobolev flows. In Lejean and Raymond work.
Okay, thank you. Thank you. Thank you very much again for interesting talk. And do you have a question?
Yes, I have one question,
Okay.
if I may.
Yeah, you can.
So I have this question. Sorry, for me, it's still very difficult to understand all details. But just to make a comparison, suppose you have something like a rough differential equation with bad coefficients, but in the rough sense, you know, which extends or which can be solved for very bad coefficients, like very irregular drift. But this is in essence, this is a deterministic theory. So my question in essence is, how much is your theory in the very end basically a deterministic completion procedure? And how much is it really related to probabilistic arguments? This is in a way my question. So let me say it like this. Suppose you have a bad ODE with bad coefficients.
Okay.
But then you can also ask for existence of flows and stuff like that.
Yes.
So does your theory also apply to bad ODEs? That's my question, I guess.
I hope so. I didn't do it, but you see that the first part is completely deterministic. So once you prove this relative compactness property, then you can complete the skeleton to a kind of flow and then analyze bifurcation points.
Yeah, so I would suggest that you include an example of an ill-posed,
Yes,
if you wish,
yes.
ODE.
Yes, it's a very good idea.
Okay, thank you.
So thank you again. And now we do not have time for questions because we have to start the next talk. So the next talk is by Professor Andrei Yuryevich Perepenko, and the talk's name is Analytic and Stochastic Description of Brownian Motions on Star-like Graphs. So you may begin, please. Your microphone is off currently.
Do you see my screen?
Yes, I see. We see your screen, and now we can hear you. Thank you.
Okay. Okay, it's a great pleasure to be in Leipzig and in Kyiv at the same time due to virtual technologies. And this is my joint talk with Adam Bobrowski from Lublin University, Poland. And today I would like to give a representation of strong Markov process, of any strong Markov process on a graph that consists of finite number of rays with a joint vertex that behaves like a Brownian motion at each ray until hitting this vertex, and then it may exit from the vertex, and when it exits, maybe by a jump, it behaves again like a Brownian motion until the next hitting, and so on. I'm going to present analytic construction of all these processes and stochastic construction. And let me start from the analytic methods. So when we construct a Markov process, there are a lot of possibilities. The classical one is just give transition probabilities that satisfy Chapman-Kolmogorov equation. For example, for Brownian motion on the real line, transition densities are just Gaussian with variance t, where t is time. If you have transition probabilities, then you can associate with transition probabilities a semigroup defined, for example, on the set of bounded measurable functions, or if the process is failure, then on continuous and bounded functions. So today I will consider only failure processes. This means that the corresponding semigroup acts from space of continuous function to space of continuous bounded to continuous bounded, and immediately, if the state space is locally compact set, we know that there is a Cadillac modification of this process, and that this process has a strong Markov property, and so on and so forth. Okay, if we have a semigroup, then we can apply powerful method of functional analysis. We can construct generator, and we know that generator uniquely determines the semigroup. Well, in case of Brownian motion, the generator is 1/2 times second derivative. Well, you have to be careful with domain. And sometimes you have an operator, and then you may show that this operator is a generator of certain Markov process. And certainly, if you have a generator, you have forward, backward Kolmogorov equations, and for Brownian motion, they are just hit equations. By the way, Fourier introduced hit equations 200 years ago without knowing theory of stochastic processes, semigroup, and so on and so forth. So you may start from that objects. And okay, one more example, one more way how can we determine a Markov process is via resolvents. Via resolvents. And there are theorems that state that in some sense convergence of resolvents to a resolvent of Markov process is equivalent to convergence of semigroups, or in some sense convergence of generators, and in some sense weak convergence of Markov processes. Well, these are analytic methods of constructing Markov processes. And if we know, say, generator or resolvents, then we can calculate some numerical characteristic of Markov process like expectations or probabilities. And now let me introduce some stochastics method. When I say stochastic method, I mean that assume that we know some basic process like Brownian motion or Poisson process or Poisson point measure. And then we may construct some other processes as a function of Brownian motion. Probably the easiest way is reflecting Brownian motion. If we know usual Brownian motion, then we take absolute value or Skorokhod reflection map. We will talk about this a little bit later. So some function of just basic process, and we get a new one. And sometimes we may obtain Markov process. Well, if we consider SDE with nice coefficients, then a strong solution to the SDE is a measurable function of a Brownian motion. So in some sense, a Brownian motion is just basic brick, and then we have certain function, and solving this method is certain stochastic procedure, and we get another, okay, now Markov process. Well, but there are a lot of other methods like martingale problem, Skorokhod reflection map, eta excursion theory, when we construct any Markov process that visits certain point as a concatenation of excursions that may have simple structure. Okay, but let's return to our problem, how to construct a diffusion on a graph. And at first, let us consider a very simple situation when the number of rays is only one. So let us describe all Markov processes on a half line that behaves as Brownian motion up to hitting 0. Well, it can be proved that the generator is 1/2 times second derivative everywhere, okay, for all x's, but this operator should satisfy certain boundary conditions that were found by Feller and Wenzel. And the domain of this operator, okay, let me consider, it's easier to consider this operator for all x in 0, infinity, and include infinity, and compactify this set. Then we have compact state space, and we want to describe all generators that have this form. And Feller and Wenzel prove that any Markov process with this generator should obey certain boundary conditions. And the statement was if and only if. And boundary conditions are of this form, where P1, P2, P3 are non-negative function. P3 is a measure that may be infinite, but satisfies this property. So it's like a Levy measure of a subordinator. Plus one additional condition that P2 plus P3 should be positive, or P4 should be infinite measure, or both. This sum is positive and P4 is positive. Well, there is a probabilistic interpretation of these parameters, like P1 is intensity of killing at 0, P3 is slowing time at 0. This corresponds to certain reflection, and this corresponds to jump exit from 0. For example, if you have only this, boundary condition, then the process is the following. It hits 0 and stay there forever. If, for example, you have only this, then this is generator of reflected Brownian motion. If you have a combination, for example, of this and measure P4 is bounded, then the process behaves like a reflected Brownian motion until the local time at 0 reaches certain level, and then it jumps, and then it behaves similarly, where the distribution of a jump is proportional to P4. Okay, there is a question how to define the process when all parameters are not 0, and we will discuss it a little bit later. Well, and when I say that killing at 0 or stickiness at 0, this is just standard procedure that we can apply to the general strong Markov process, and assume that this process visits certain point, for example, A, with the positive probability, and that semigroup generated by X is not so terrible, then it's well known that there is a local time at A, certain additive functional that may increase only when the process visits this point. And the way to kill process and to obtain failure process from X is this. We take an exponential random variable with a parameter gamma, and if the local time at A is less than tau, less than this exponentially distributed random variable, then the process behaves, okay, now A is 0, behaves as initial process. And when you reach tau, then you kill the process, or, for example, send it to infinity or to some special graveyard point. Well, to make the process sticky at a certain point, the procedure is this. You have a local time, you multiply this local time by a certain positive parameter, and we consider this continuous additive functional, and actually this function is strictly increasing. So the inverse function is well defined, and then you make the transformation of time in original Markov process. Then it's well known that you obtain again a Markov process, and the transformation of local time is again a continuous additive functional of this process with stickiness at A. By the way, if original process has no sojourn at A, so spend 0 time at A, for example, like Brownian motion at 0, it can be shown that alpha times this composition is just time spent at A. So this sticky process spent positive time at this fixed point. By the way, if L was a symmetric local time, it can be seen that this image, this composition is again a symmetric local time of this sticky process, but you have to be careful. You have to exclude 0 from the integration set. Well, but on the other hand, you also has this representation. So you have both description of a new additive functional, and then you can combine this scaling and slowing time at point A or at 0, and then you can kill again and make stickiness again. By the way, this transformation commute if you use this local time after you make the process sticky. Well, so we discussed stickiness, how to make the process sticky, how to kill it, and another transformation is jump exit. The procedure is the following. You have a process, you have a local time, well, assume at 0, and you accumulate the local time at 0 until it hits a certain exponentially distributed random variable, and then you jump. You jump with certain distribution. Then you again accumulate the local time, and then you jump with the same distribution independently of the past, and it was proved by Akeda, Nagasawa, and Watanabe in 60s that again you obtain a Markov process. And by the way, it can be easily seen that if you concatenate local times of the process before the first jump, before the second jump, before the third jump, and add them together, then this new functional is again a local time of a new Markov process. And if these local times were symmetric local time, it can be easily seen that this new local time is again symmetric local time. Well, and now you can combine killing, stickiness, and jump exit with finite measure. And this is a way how to construct a new Markov process from the previous one. By the way, it is easy to calculate a resolvent of the new stochastic process in terms of resolvent of killed process and Laplace transform of the moment of killing. And killing means the moment of jump. The moment of sigma is a moment of jump. Okay. And when we discussed one-dimensional diffusion, we discussed reflection. And again, you can take absolute value, but let me discuss procedure proposed by Skorokhod. He proposed to consider so-called reflecting map and to consider some reflecting problem for any continuous function w such that w of 0 is non-negative. Skorokhod proposed to find a pair x and L of two functions that satisfies the following property. X is a sum of w, so w is like a noise, plus certain function L, which is continuous and non-decreasing, such that x, the sum of w plus L, is again non-negative. This is important. And this function may grow only when the process X, this unknown process, hits 0. So at first you behave as W, then, for example, W say, okay, please go down, and the process L is like compensation. It says, okay, go up such that you stay near 0. And when the process W say go up, then effect of L disappears and increments of L is 0 when the process is positive. Well, it was proved by Skorokhod that this problem has a unique solution for every function W. Moreover, it can be proved that there is expression L is so-called running minimum of W, and X is just sum of W and L. Well, as I said before, when we discuss reflecting Brownian motion, you may take just absolute value and not Skorokhod reflecting map. And if you look at the semi-group, you can easily prove that the semi-group which is that corresponds to this Neumann boundary condition. You can see that its transition density is this, where phi is Gaussian measure, and it corresponds to the following transformation of a Brownian motion. However, it was proved by Levy that the pair X and L are solution of Skorokhod reflecting problem for a Brownian motion has the same distribution as absolute value of a Brownian motion and its local time at symmetric local time at 0 that is defined as follows. So Skorokhod reflecting map really gives a reflected Brownian motion, and it corresponds to these Neumann boundary conditions. I also want to mention that L is a continuous function of a noise, but the local time actually is not. And another question is this: okay, is there reflecting map? If we want to combine jump exit from 0 and continuous reflection, and there is corresponding definition similar to Skorokhod. We have two functions W and U. U is strictly increasing, and we want to find X non-negative, and this L that grows only when this X hits 0. And it can be proved that there exists a unique solution, and there is a formula. Moreover, if U is a continuous strictly increasing function, then this term disappears, and we have Skorokhod formula. However, if U is discontinuous, then this composition U and generalized inverse is non-trivial. Well, and now I would like to recall a result by Ito and McKean, who gave a probabilistic formula for semigroup with this boundary condition. And there was some conditioning, killing, stretching at time, like here, plus some formula where you have a subordinator and its inverse and a local time. However, you have this strange term minus local time and absolute value of a Brownian motion. However, if you remember Levy theorem and if you change this absolute value of a Brownian from the previous slide, it can be seen that the following result, the following process give a representation by eta and McKean. So Brownian motion plus, so this is generalized reflection, this is time stretch, and this is scaling where zeta is exponentially distributed random variable. By the way, it can be proved that this process is a local time of x. It's a local time at 0. And now, okay, I have probably 4 or 5 minutes. I would like to give representation, give the answer for the process on a graph. The process on a graph, well, probably it's easier to consider not the graph, but just several half lines, and you say that, okay, we identify the origin. And the first result is that the boundary conditions must be the following. So Laplace is just 1/2 times second derivative. You have first derivatives at 0 of each fi is just i's coordinate. You have to have some measure m with this property, and actually to prove that this theorem, we verified Heliosida theorem. Moreover, we calculated resolvents of this process, and resolvents are explicit. Here, R0 is this operator, is a resolvent of the Brownian motion on a half line that is killed when the process hits origin, and you have a certain integral representation here with concrete formulas. And the question is how to give, is it possible to give stochastic representation for this process? And the answer is yes. So let me formulate the final result. Okay. Assume that you have certain positive, non-negative numbers, alpha, beta, gamma, infinite measure m on this graph that satisfies this property. M Brownian, independent Brownian motions. Mi is just running minimum of i's Brownian motion, and you have process with independent increments where n is a Poisson point measure with Levy measure, oh, excuse me, not mu, but m. It can be seen that all coordinates are independent subordinators. Okay, and assume that you have exponentially distributed random variable. Then the statement. There are unique non-decreasing functions, T1, T2, Tm. It's like time transformation that satisfy certain balance condition. Actually, this process was a local time in Eta and McKean theorem. So this statement is like balance of local times, and the process with this generator is the following. You take Eta and McKean process at this time Ti, then you slow it when the process hits 0 according to local time, and sometimes you kill this process. And it can be proved that this process corresponds to this boundary condition. Moreover, these processes, these common values, are local time at 0. Okay, and probably that's all. Thank you for your attention.
Thank you very much. Are there any questions?
Is there any paper where it is written already?
Not yet. So we almost finished this paper, and I hope that we will finish the paper maybe in a month.
Okay, we are looking for.
So 60 pages or maybe 70 pages are written.
Okay, we are looking for.
We just polish some details.
Perfect.
May also I ask?
Yes,
Max,
yes.
you wanted.
No, Vitaly, go ahead, please.
Okay, thank you. I have only the question about the behavior of that process, because I'm familiar with the paper of Bayraktar that you
Yes,
exactly
exactly.
It's very quickly because of different reason, because the constructions that they use also are used in our paper.
Yes. Actually, the building block of my process is Walsh-Brownian motion. And Bayraktar, actually, his result is that Walsh-Brownian motion behaves as the following. You start reflected Brownian motion on each ray, and you think about time that you spent. And these times, so he selects these times in certain way, such that local time of this reflected Brownian motion and this are proportional according to probabilities selecting each ray. Yes, and we apply this result by Bayraktar, yes, as a building block.
My question is, if I may continue, is about the jumps, how jumps is organized in your construction. If the Brownian motion moves according to one line and goes to 0, then here the jump is allowed in any direction, or according to your construction, it will be also in the direction of
jumps
the line.
Maybe only in the direction of line. So jumps must be on the direction of line. So you live on this spider.
Okay, so therefore you cannot like randomly choose another direction and jump.
You may jump onto another. Maybe it's easier to make a picture. Yeah. So we have independent Brownian motion with reflections. So red means this line and green means this line. Okay, sometimes it's reflect continuously. So we may have both continuous and jump exits. And then we consider a time. So sometimes you apply this, sometimes you apply this, and concatenate them together. So we have like red trajectory, green trajectory, red trajectory again, but we have to count the time that you spent here and here. The total time is t, and you have to have balance between times in red mode and in green mode.
But I just worry whether you can move between different lines because of the reflection or because of the jumps.
Because of both. Because of both.
It was my question.
So it's easier to think about just one-dimensional process that is colored in different colors. So you cut this, and then piece them together in certain order and obtain the new process.
Okay.
The question, the things which happen in 0, do they commute for these operations?
Yes, yes. Okay.
I mean, the construction, when you reflect or when you jump from the...
Yes, you may start from Walsh-Brownian motion, then you may kill, then, okay, well, killing, stickiness, and reflection commute, but continuous reflection and jump reflection do not. So it's like in this generalized Skorokhod problem.
Okay, thank you. Maybe very short question.
Yeah, can I see your references again, please? Because I was just wondering.
One moment. Okay.
Okay, so I mean, there is a group of German mathematicians, contemporary, like Robert Schrader, well, Vadim Kastrikin, and
yes, yes, Kontrikin, Podhoff, yes, we make references. Maybe I forgot here to mention them. Yes, I know the paper.
They have a special case, yeah? Kastrikin, Podhoff, Schrader.
Yes, they have a special case, continuous exits.
Jumps.
Without
the jumps. Yes. Okay, thank you.
Okay, thank you very much. And now we have to switch to another talk. Talk will be by Vitaly Konorovsky, and the title is A Quantitative Central Limit Theorem for Simple Symmetric Exclusion Process. Please, you may begin.
Okay, thank you so much for the possibility to give the talk. I would like to tell you about the result obtained together with Benjamin Guess that we like a lot. And it will be about the speed of convergence in the central limit theorem for the simple symmetric exclusion process. And I would like to start, I want to start with the description of the model. We will work on the torus. So at the beginning, let's consider d-dimensional normalized torus, and we consider partition of the torus by points k divided by n. So the distance between different points is I mean, in every direction is 1 over n. And also assume that at every point or in every slot, there could be maximum one particle. So there could be the situation that there is either there is particle or there is no particle. And here I sketched what one particle configuration, red color, or so the colored circle, it means that in that specific slot is a particle. And then the dynamics looks as follows. Every particle, independently of each other, waits the exponential time and then makes the jump. And jump is looks as follows. It just chooses a random direction and jump to the neighboring point. If the point is already occupied, then nothing happens. When I say nothing happens, this can be also interpreted in different way. We also can say that two particles just interchange each other. Since we don't keep any marking of particles, these two types of behavior, that either particle do not jump or just interchange the position with a particle that is in the slot where the first particle wants to jump, so it is the same. Then to describe the particle configuration, we will use eta. So eta, it will be the element of this space where eta of x is equal to 0. It means that at slot at site x there is no particle, and 1 if there is a particle. And also to describe the behavior, mathematically describe the behavior, we will need the following notation. This notation will mean that the information that is, or the slot that x and slot y are interchanged. So if, for instance, if there is a particle at point x and there is no particle at point 1, this will mean another configuration where the particle from slot x is jumping to the point y. But if it happens that there are two particles, then they just will interchange their positions. And using this notation, we can write the generator that is well known and has this form. I just want to pay your attention that usually in the literature, people consider the case where the distance between sides is equal to 1 and exponential clocks are have rate 1. So in the generator that I wrote, the system is already normalized. In particular, the time, the space is scaled like 1 over n, and time is scaled as n squared. And later we will work with this generator. Also, about the initial condition, we want to consider the case where particles start from random configuration. And we will describe it as follows. We fix a function ρ0, which will describe the initial profile of particles in the case when you already pass to the limit. So you have some function ρ0 on d-dimensional torus, and then you assume that, or you put a particle at time 0 at site x with Bernoulli distribution according to the value of ρ0 of x. So it means that you put the particle with probability that is equal to ρ0 of x. And you do that independently for every slot. The simple observation that also will be important for us for the understanding of what is going on later is the following. Actually, we can ask about the expectations of particles and how it is changed. And using the martingale problem for particle system and computing the expectation, you will come to that the expectation should satisfy this equation, where delta n, it is a discrete Laplacian on the discrete torus. And then considering the empirical distribution associated with this process rho n, and passing to the limit, and taking into account that rho n satisfies this equation, we can come to the following observation that the limit will be a solution to the heat equation. And by the way, later also I will, so the solution of the heat equation started from this initial configuration. Also, sometimes I will use this heat semigroup denoted by PT heat equation here. And now keeping in mind these results that the expectations of particles or empirical distribution of expectation should converge to the solution of the heat equation, it is not at least complicated to predict that that if you have too much independence in the particle system, that probably you have the law of large numbers, and then after the rescaling, after the sending n to infinity, you will have the convergence to the solution of the heat equation. And it is about that is the following result. In particular, if you consider the empirical distribution for the particle system, so it means that now you consider on the discrete torus, you put masses 1 over n to the power d at every point where is the particle. And then this measure will weakly converge to the solution of the heat equation with the initial profile that is equal to ρ0. The proof of this fact is, I would say, it is not complicated. It is based on martingale approach. Everything, what you need to do, you just need to write the martingale problem and see what happens with the generator when n goes to infinity. And in particular, when you consider the generator on the cylindrical function, where I denote by this bracket the integration of function phi with respect to eta, empirical distribution eta tilde, then you will see that, okay, according to the definition of generator, it is that, but then using the Taylor expansion for the function f, you will come to this term, and then you will have plus higher order terms. And you see when n will goes to infinity, the term that includes the second derivative, it will goes to 0, and you will have only in the limit like that object where delta n converge to the usual Laplacian. That gives you, roughly speaking, the martingale problem for the solution of the heat equation. And this explains the result. Then after that, you can ask the question, okay, what is the fluctuations of particles around their expectations? So you can subtract the expectation and normalize it. And when you do that, and when you consider the empirical distribution, then you can do the following. You can also write the generator, write the Taylor expansion. But now only the difference will be when you will write the generator for eta, computing the derivative of your function f, this n will appear. And in the first term, it can be combined with eta and will give you also the fluctuation field. But for the second term, when you compute two derivatives, then you will have n to the power d that will be cancelled with n to the power d that you saw on the previous slide. So therefore, now you will have one additional term that will not be vanishing. And again, passing to the limit in the martingale problem, you will see that, for instance, when you consider only the cylinder, only the integral of function phi with respect to this empirical distribution, then the drift that will be described by that term will converge to the corresponding term that you can see from the heat equation. But then the quadratic variation that is described by that part of the martingale part, so we'll have this form. And at least on the formal level, you assuming that this eta converge to their expectation. By the way, I didn't pay your attention that this tau j, it means only the shift of the particle of the function of the configuration in the corresponding direction. Then assuming that their convergence, you can predict that, okay, this converge to rho, this converge also to rho, so therefore you will have two rho that will be cancelled with Z2, and this product may be converged to the product, and then you will have a rho minus rho square. And it is the reason why one can obtain the following central limit theorem that says the following, that the fluctuation field that defined as an empirical distribution will converge in the space of distribution to the generalized Ornstein-Uhlenbeck process described by this equation. So in particular, the martingale problem associated with the solutions to this with this equation, it has exactly this form, roughly speaking. And the initial, since your particles initially started from random points, also you will have some fluctuations for the initial conditions. Therefore, you will have the solution starting from some Gaussian initial condition with these covariance. But now it is not so important for us. And our main goal was to answer the question how fast the fluctuation field converges to the Gaussian process. Now you cannot consider the difference and say how fast the difference goes to zero, because these objects live on different, they can live on different probability spaces. But we can ask about, we can test the fluctuation field by some function, for instance, by cylindrical function, take the expectation and compare this with the corresponding expectation for the Gaussian field. So today we will ask the question about the rate of convergence of this difference. And here the problem to answer that question is that the theory which was proved this result, it was based on the tightness argument and the Holly-Struck theory for solutions of this equation. And it doesn't give the answer what is the rate of convergence. We need to use something else. And here I would like to mention a few also results where people ask a similar question. And for instance, in the work of Guess and Zank, they showed they also consider the similar question, but only for solutions of stochastic differential equations with singular coefficients, and they got also the rate of convergence, but in that case they works with objects that lives on the same probability space, so therefore analysis was completely different. Also, there is an interesting work about the higher order approximation of Dean-Kawasaki equation, but it was used a lot on the duality argument, and the structure of noise was really important, and we also cannot use this approach to our situation. But we will somehow follow the approach from that works about the quantitative propagation of House result, and also the central limit theorem for Smolchowski coagulation model. So here the used approach is based on the comparison of the generators for that for stochastic object. That also we want to do, but in our situation the model is much more complicated, and one need to put much more effort to get something reasonable. The main result that I want to present today is the following, namely, if we consider the particle profile that is quite smooth. Now we consider the particle system that start independently at every point according to the Bernoulli distribution with this given by this initial profile. And when we consider the fluctuation field, then and also a solution to this Ornstein-Ulbeck equation that you saw from previous slide, then the rate of convergence is like that. It is 1 over n to the power 1 minimum d divided by 2. Probably you would say that, okay, this error is not very optimal because you have this minimum 1 that one would not like to see in the rate of convergence. But here the main problem is that this one, it appears from the latest discretization error, and we cannot improve that. And later in my computations, you will see that we will need to compare the discrete derivatives with continuous derivatives, and it is exactly the error that appears there. So therefore, if you want to have a better rate of convergence, probably somehow you need to change this object, just adding some additional terms that also depends on n, and that somehow you could compensate this latest error. Now about the approach that we used, and so here the approach is the following. If you have two Markov processes, we start from the same initial condition, and their generators are defined by this G and semigroup associated with the processes by P. Then the difference between expectation can be computed as a difference between as an integral of this expression. And this is a semigroup associated with one of the processes. So therefore you can rewrite it differently. You can just write that it is an expectation, and here just plug in so here you have the semigroup, and this semigroup you can write differently, just replacing by the expectation, and here just put in this difference the process X. So therefore now to apply this result, we will or to find the difference or estimate the difference between expectation, everything what you need to do, you need to consider the semigroup associated, for instance, with the process Y, then compare two generators on this semigroup. The comparison could be pointwise for every fixed state of XS. After that, when you get estimate, probably depending on the points, so on the states X, you need to plug in X, and then you need to estimate or compute the expectation. And the error or the constant that you get, it will be exactly the error between the difference of two expectations. And we want to realize this idea, but one of the, and we will apply, so we want to consider the fluctuation field as a Markov process. But here the problem is that the fluctuation field itself is not a Markov process, as a homogeneous Markov process. We need also to take into account the expectation of particles. So therefore we consider the pair. It will be our one process, another process, it is the limiting object. And also we need to we need this, or we expect that this object start from the same initial conditions. So therefore, but it is not the case in our situation. Therefore, our idea is the following. Okay, we consider the particle system. Then we consider the associated Ornstein-Uhlenbeck process started from the particle configuration that I denote this by additional, I put here n. And then we need to make the comparison between particle system and Ornstein-Uhlenbeck process. And then we also need to compare two different Ornstein-Uhlenbeck processes starting from different initial conditions. And then just using the triangular inequality, we will get the estimate of the needed estimate. So this second part, it is not interesting because here is a question about the comparison of two solutions of the same equation starting from from different initial conditions. I would like to focus on the first case. When you have a solution to the stochastic differential equation started from the particle configuration, and you have the fluctuation field of the particle system, and you want to compare them via this formula. And just very quickly, just doing a similar computation as we did before, you will see the same term as we saw for the generator for the fluctuation field. It has this form, and this is the generator for the particle system. And now when we will write the difference for the function f, by the way, at the beginning, I consider the f that is a cylindrical function, only for simplicity of computations. You see that, okay, comparing this term with that, it is not a big problem because it is just a comparison of discrete differential operator with continuous on the test functions. Only the problem is to comparing these terms. Because of the following reason. First of all, if you consider, you remember I told that you need to compare the generators on functions at the particle at the configuration of one of your processes. So here's the process that we must consider. It is your particle system. So therefore you need to compare generators on the empirical distributions because particle configuration is described by empirical distribution. But now, so therefore this rho tilde, it has to be the empirical distribution, and rho square, it doesn't make any sense. It is the first problem. The second problem also is not clear what to do with that because of what I said. So there is no sense. This doesn't make any sense. And also, even if we can make some sense of that one, also it's not clear what to do with this difference. Another problem is that actually we need to compare the generator not on the cylindrical functions, but on the semigroup associated, in our case, with the Ornstein-Uhlenbeck process that is not cylindrical function. Also, the problem is that because of this term in the equation, the Ornstein-Uhlenbeck process is not Fréchet differentiable as the empirical distributions. But we need that because you saw that in the generators you saw the derivatives of the function. So you need some kind of the differentiability. So therefore, and just taking these all facts into the account, we need somehow probably to change our lifting of particle system, not considering the empirical distributions, but considering something else. And in the rest of my talk, I would like just to say a few words how we overcome that problems and how we obtain the result. Alexey, could you tell me how much time I have, because I didn't pay any attention when I started.
I think you can have at least 5 minutes, maybe.
5 minutes. Okay, yeah. Thank you so much. It will be enough. So here the idea is the following. Look, we work for particle system, we consider the discrete torus. For the limiting object, we consider the continuous torus, and we would like to put them together somehow. And here the idea is the following. Let's consider so the particle configurations. Like when you only consider the particles at slots, you can consider them as, say, L2 functions on the discrete torus. And you can introduce the inner product, which I denote like that with index n. And we can also consider L2 functions on the continuous torus with on the inner product. And then the observation which we use is the following, that actually these two spaces have, I would say, the same basis. Namely, if you take the exponents, so therefore this is the basis for that space, but then you need to take a finite number of elements here, and also it is the basis for that for the L2 space. So in particular, every function you can write as the expansion of according to that basis, but you need to use a discrete inner product. And for continuous case, you can use a continuous inner product, and then you will have this expansion. And therefore, here the main idea is that having the function defined on the discrete torus, we can write the expansion of this function, and you have the equality for every point of the torus. But now you see that the right-hand side, it is well-defined function on the complete torus. And then you can say, okay, we extend this function rho from the discrete torus to the continuous, just taking the right-hand side, just taking this expression. We also need a companion that is a projection operator, where you just take these inner products, like the expansion on L2, on the continuous torus, and you just cut off everything. So you consider the same amount of basis elements as in that set. And the nice property is that we want to use is that actually now you can nicely jump between two different inner products, because just considering functions on the discrete inner products, you can replace that by a continuous inner product, just replacing this row by the extension. It is a simple computation. Or if one function is from the discrete space and another from continuous, then considering the inner product of this discrete function with projection of the continuous function, you can replace by the continuous inner product. And this freedom gives really a lot of possibilities to manipulate, to go from the discrete word to the continuous word, and so on and so forth. And so therefore the idea was to replace the empirical distribution by this expansion using the Fourier transform. Therefore we use, instead of the empirical distribution, we use this discrete Fourier transform that we extended, and we do the same for that Gaussian field. And now you see that if you consider this lifted object, if you test by function, because of this property that you can jump, you can move this extension operator to the test function, and then you will have the discrete product. But this discrete inner product, it is exactly the integration with respect to the empirical distribution. So therefore, everything what we computed before, so you can use, because only everything what you need to do, you just need to replace your test function by the projection of test function. And actually we do that. So therefore you will see the projection, but here you need to be a little bit careful writing these generators, because when you integrate this Laplacian of projection with respect to this new lifted element, also you can remove this element, you will have the discrete inner product, but when you want to continue, go back to the continuous, you need to put here the extension. So therefore here you will have some additional things. And now also another thing that we use in our comparison is that this basis is eigenvalues, is eigenvectors of the discrete differential operators and continuous differential operators. So therefore, this difference you can easily estimate using the difference between the corresponding eigenvalues. And by the way, now this term, it will make sense, because you will have like rho, which is now smooth, and rho square is smooth. So therefore you just need to go carefully through every term. You need to carefully estimate of everything. In particular, you will have also one strange term which will include the product of the fluctuation fields, but we can use here that the fact that that the correlation between different particles can be nicely estimated if particles are different. So therefore we can come to the estimate, to the night estimate, at least for the cylindrical test functions. But this everything can be nicely generalized now, because these objects can be considered on the corresponding Sobolev spaces to the functions that are Frischer differentiable on the Sobolev spaces. And now the second step, everything what you need to do, you just need to show that the semi-group associated with the Ornstein-Uhlenbeck process is quite regular. So therefore, we also can prove the differentiability. So therefore, now the comparison of generators can be done on the semi-group associated with the Ornstein-Uhlenbeck process, because it is like quite smooth, needed for our estimates. And this leads us to the estimate, to the error that you saw in the formulation of the theorem. Okay, thank you so much for your attention.
Thank you very much. Do we have any questions? Yes, please.
So I have one question and one remark. So the remark is absolutely unnecessary, but since I was pointed to this, I think this formula that you used and this perturbation formula, which is your basis for your analysis, we used a similar formula in a different context, and I think there is a name for it. It's a version of this Duhamel formula. This is just, you might look it up. It would be nice. The perturbation formula for semigroups. If you have two semigroups and you want to compare the two, then you can basically do some kind of so please look it up. I think I just checked it. I think it's true. It's also true in my case. So if you want to use the name for it, it's the Duhamel formula, I think.
Some people call this Cathode-Rotter formula.
Yeah, it's all the same. Yes.
I didn't see at least this formula with that name, but I know that they call it. And by the way, you can find it on the probabilities lemma 6 in the A.V.Skorokhod book. So when we discovered that formula independently, we just found it in the book of A.V.Skorokhod.
I'm sure that, but I wanted to do it. This was a Russian-style remark, right? If you make a remark that an author did not use the proper name, anyway.
Yeah. Thank you so much. I will take a look.
The second question is, well, first of all, okay, I should have said I like the result. I like the project. Thank you for the excellent, interesting talk. One more comment just comes to my mind. I wanted to offer it. So the limit process, the limit thing is Gaussian, right? So in a sense, right? So it's an Ornstein-Uhlenbeck process and some infinite dimensional space. So it's a Gaussian object. And I just hear from other contexts that people like to do central limit theorems quantitated by some version of Stein method. I mean, one could look at it and just as a proposal, just do some version of a Stein method for this object. This is another approach. Did you think about that, or is it just?
Yeah, I mean, we thought a lot about the dynamical approach using Stein method, and then we were somehow failed. But when we discovered this approach via the comparison, and also, for instance, you can see this approach that you mentioned was used to find the rate of convergence, for instance, of random walk to the Brownian motion, where was used exactly this idea that Brownian motion is invariant distribution for infinite dimensional Ornstein-Uhlenbeck process. We cannot repeat that, but when we started to work with the generators and saw how the Stein method is obtained, so therefore it is like these two approaches are a lot related to each other. But this result gives weaker estimates because you do that for every fixed time. So you cannot do that pathwise as you would can, for instance, considering the Stein approach.
Okay, thank you.
Thank you. Any other questions? Okay, so then we have to end this session. Thank you very much again to all the speakers. And we meet again in 1 hour and 11 minutes, so 15:30, right? Okay, goodbye.
Thank you.
Thank you. Bye.